Okay, Assalamualaikum warahmatullahi wabarakatuh. So now let's continue the last part of the fabrication part 2. So that is what we call sputtering. So in the last video you learned about the PVD, right? So we have two types of PVD. The first one is evaporation and the second one is the sputtering. So for this evaporation is usually for metal evaporation where you need a very high temperature in order for you to vaporize the source to be on top of the substrate. So let's move to the second part, that is sputtering. So sputtering is you are going to bombard your atom to become ionous ion, and then this ion will go to your source and will be bombarded to your surface of your substrate. So there are four types of sputtering. The first one is DC, RF, reactive, and magnetron. Okay, what is actually sputtering? So at first you have a target material. So let's say you're going to sputter zinc oxide. So your target will be zinc oxide. So when you have your target material, so the surround of your target will have what we call inert gas, that is argon ion. So this argon ion will be have a lot of energy to hit your target. So once it hit your target, then you will have a momentum to transfer the target atom on top of your substrate. So who are going to hit your target is what we call unreactive ion. So this is come from the inert gas. Why will you use inert gas? Because it will not react with your target, right? So you will knock off the material by the momentum transfer. So what are the example of the target? Usually we have piezoelectric such as zinc oxide, dielectric, or metal. So there are different methods to obtain the energetic ions, where this is the argon ions. So some of them are magnetron, DC, or RF. So for this part, it is actually less directional and it's actually faster than the evaporation, because you have extra energy that is coming from these ions to bombard your target, and then it will be sputtered on top of your substrate. Okay, so if you see the explanation here, in order for you to do that, you need to make sure your chamber is in vacuum, so it can lower than the atmospheric pressure. So then you need to apply a voltage so that the target is scattered and the substrate is ended. Okay. In between your target and your substrate is a chamber. So we need to make sure this area is what we call plasma. What is actually plasma? So plasma is the ionized, is created by ionizing a sputtering gas. Sputtering gas means here is the argon just now, the inert gas. So in order to have an ionized gas here, you need to make sure you're making in chamber and with a certain pressure. Okay, so why is having ionized gas here? So it can easily bombard your target here, and then it will be deposited on top of your substrate. So the substrate, the sputtering process occurs when the target material is bombarded with the sputtering gas, that is the inert gas, and will result the energy transfer and cause the target particle to escape and deposit on top of your substrate. So let's see the simulation. The left is the evaporation. So you're going to have like resistive heating, and then it will be vaporized the source and goes to your substrate. So it's like a one-way process. But for your sputtering process, so you need to have what we call here plasma. So inside the plasma is the ionized gas of the argon. So this ionized gas will have a lot of energy, right? So it will move and then bombard your target here or your source here, and then this let's say this is zinc oxide. So this zinc oxide atom will deposited on top of your substrate. So let's see again. So this is your plasma, which we have the ionized argon. So you bombard your target and deposit on your substrate. So why you need to use argon or inert gas? Because it will not react with your target. So if the gas react with the target, you cannot get the pure target that is deposited on the thin film. Why argon? Why not other type of inert gas? Because helium and neon are much more expensive than the argon. That's why we use argon for the sputtering. So the one that we are talking about the plasma just now is this one, is the purple color. So if you have some chance to go to the sputtering lab, so you can see after the vacuum, the chamber has been vacuumed, there will be a purple color. So this purple color is actually the plasma. This plasma make the gas conductive, and then it will generate the ions, the argon ions. And this argon ions is having a very high energy, and it will be accelerated to strike the target. Okay, so this plasma contain a number of positive argon ions and electrons. So typically only 0.01% atoms are ionized. So we need this purple color of plasma before you can start the sputtering, to ensure that your ion has a very high energy to give impact to the target. So the first type of the sputtering is what we call DC sputtering. So in order for you to make sure that your argon is ionized, so you need to connect to what we call a DC supply. So this DC supply is very high voltage. It will be connected to either cathode and to the anode. So it will be energize your argon inside here to become a plasma. Okay. Source material must be conductive. So in this part, your target must be conductive in order for you to do DC sputtering. So we have other type of sputtering that is called RF, reactive and magnetic sputtering. So inside your RF sputtering, when you apply AC voltage, the frequency is more than 50. For this RF, you don't need to make the target. It can be not conductive, okay, but the chamber also will be sputtered. For your reactive sputtering, so let's say you want to have zinc oxide, so your target can be only zinc, and then you're going to insert oxygen. So your substrate, this oxygen will be react to the bombard target, and your output at your thin film will become zinc oxide. So this is what we call reactive sputtering, where it will react to the target to product that will be formed together and form the zinc oxide. So it's a quite difficult procedure here. And the last one is the magnetosputtering. So we use magnet here to ensure that your ionized is having a path. So when you have the magnetic field, so it will go to the path accordingly. So it will increase the ionization at the cathode and leads to the higher yield. So this is the example of the magnetosputtering. So your ion will be goes to the magnetic field. At a certain part, it will be increase the ionization rate. Okay. So the comparison between the evaporation and sputtering. So for your evaporation is for the lighter element and simple compounds. For sputtering, you can sputter anything as long as you have the target. The target is quite expensive. And for evaporation, it's a low energy ions. Sputtering is high energy ions. And for your sputtering, it will give a better quality of the thin film, such as you have a smaller grain size and good adhesion and a dense film. But for your evaporation, usually we do for metal evaporation, the grain size will be quite large and less dense. In terms of the vacuum, for sputtering, you can use a very low vacuum up to only 10 power of minus 2. But for evaporation, you need a very high vacuum which take a long time. And for directionality, this one is sputtering is having a good step coverage compared to the evaporation. Okay. So now let's move to the CVD. So what is CVD? CVD is using this gaseous solution. So it's a technique using the chemical reaction. Your source will usually use a gaseous source. So there's a lot of gases here, gas 1 until 4. So it's usually done at the very low pressure, that is 300 millitorr. Okay, so depends on the material that you want to deposit. So for your silicon oxide, it's around 450, but polysilicon is having higher temperature. So you're going to connect your gas inlet at the left side, and gas will be exit on the right side. So this is your wafer. So how it react? By the chemical reaction. So let's say you're going to have the polycrystalline. So this is you're using silicon silane or HSiCl3. So there is a byproduct. There is a hydrochloric acid and a chloride. Okay, so you insert by the gas phase transport, there will be some chemical reaction in between. So what are the difference between PVD and CVD? PVD is much more simpler compared to the CVD because it does not involve any chemical reaction. And for your CVD, you will have a hazardous byproducts, but not for PVD. For CVD, you're going to have a very high temperature and you cannot deposit on top of many layer. But PVD it can be done in air. The lowest one is at room temperature. For PVD, you need to have a high vacuum. And for CVD, LPCVD is the most common, which is the vacuum is 300 milliliter. Okay, so last part is electrode deposition. So this is the basic process to deposit the metal. So you have two electrodes, left and right, and you have a solution. So the reaction between the cathode and anode will have something deposited at the anode. At the cathode. Okay. So the reaction, you give the electron because it's called electron. So something will be deposited here by having a Cu2 plus here. So this is a we don't need to use this at the clean room, so it is as inexpensive, but the quality is worse compared to the PVD. How about the spin casting? So the substrate will be spin, and you're going to drop your source on top of your substrate, and then it will be spin. So this is what we call spin coater. And the most advanced fabrication is the Liga process. So this is just for your additional knowledge. This is for high aspect ratio. Let's say you want to fabricate a micro gear here. So it combines between the lithography, forming, and the molding. So the process are below. Okay. So this is the example of the Liga micro gear, which is very small, done by the Liga process. The last one is the most important part, is what we call etching. So etching is we need to remove something. So we have two parts. One is the wet etching and another one is the dry etching. So the wet etching is a selective process and usually used for the main fabrication but not for the IC fabrication. So you just need to dip your device into the solution of the etching. It will be etched selectively. But for the dry, you need to use equipment that is what we call RIE and DRIE. So usually you need to use gas here to do the etching. So the most simplest part is the wet etching. So you have a chemical bath here. So this is the etching solution. So once you have done your photolithography process, so this area will be softened, right? So the area that is softened, you put inside the chemical etcher, so it will be etched away. Okay, so there are two types of the etching. So one is what we call isotropic, and another one is anisotropic. So isotropic means that it will be etched from all directions. So before you do etching, you need to do photolithography first. So it depends on your mask. So for here, it's actually the positive resist. So it will etch at this area. So if you use isotropic, it will etch at all area at the same rate. So means the Y and X acceleration will be at the same rate. But for the anisotropic, it will be etched from one direction. So you can have a straight line here. So it depends on the application. Either you will have isotropic or anisotropic. For the etching selectivity is the ratio of the etch rate of the target material being etched to the etch rate of material. So previously we have learned about the etch stop layer, right? So it will stop at some part. It will not continue to etch. Okay, so the selectivity of the mask is quite important. Okay, dry etching is using the equipment machine that is RIE. So this is expensive etching techniques, but it produces a more consistent result and easier to control. So you need a plasma for this dry etching. So you need to put your device inside the vacuum. You need to put inside the gas. So it's like sputtering. Your gas here is a reactive ion, so it will be react to your solution and will be etched accordingly. Okay, so that's all for the etching part. And please go through all the slides and we will discuss next week. Assalamualaikum.